guys, welcome back to my video. So this is Learning Mentor, and in the past video we created a spring. Now it's time that we analyze it in ANSYS. So let's get started. So previously we had a problem statement over here which said that we are going to have a load of 20 to 50 newtons and 2750 newtons of force. In the end, the maximum deflection would be 6 millimeters, and we designed a spring which has a permissible shear stress intensity of 420 amperes. So we have to just see that what shear stress is in our spring. So there is an unfortunate problem here in this problem statement, that we don't have any material properties over here. We only have the shear modulus over here, which is G, 84 kilonewtons per millimeter square, or modulus of rigidity. So we have to suppose a material, and I am going to suppose the easiest material which we can all understand and have in ANSYS, which is structural steel. So we are going to suppose the material as structural steel, and we are going to apply a load of 2500 as an average, and we are going to see what shear stresses are produced in our created spring. So let's get started. Now I am going back to my spring, which you can see over here. Now we are going to convert this into an IGS file, which we can later import via an workbench. Now let's convert this into an IGS file by just save asing it. I have already done it. Now let's save it. Now it's been saved as an IGS file on my desktop. Now I'm going to open ANSYS workbench. I'll make sure that I close my SolidWorks so it doesn't use my resources. Now let's create an structural work system. It takes time. Now in engineering data, by default there is an added of structural steel, but we can add material. But as we don't have sufficient data, we cannot add material. So we are going to go with the structural steel. Now click on the geometry and right click on it and import geometry. Browse for your file. I have saved on desktop as spring.igs. The geometry will be there. Now right click on it and edit geometry in design modular. The design modular is starting, which is over here showing a red light. Now it's ready. Let's generate our created image. Now as we can see, our spring has been loaded into the ANSYS mechanical design modular. Now we have a problem over here that we can only select the top body and the whole spring is being selected. The issue that comes over here is how do we apply forces. There are two approaches over here. That is, we can create a circular surface over here and then apply load via it, and also we can fix the bottom. But we are going for an other approach, which is we will split this into multiple parts. Now to do this, we are going to go into create, then we are going to slice this object via plane. Now the plane I'm going to select is XY plane and apply. Now let's generate. Now we can see that our spring has been divided into multiple parts, which we can make many choices of forces. Now previously we could not, now we can. Now just close design modular. Now let's open ANSYS mechanical and apply forces and mesh to it. Let's do the main stuff over here. The mechanical is starting, which is shown by the red. It will take some time to load into mechanical. Now as we can see, our spring has been loaded. Our split spring has been loaded into our mechanical. Now let's create a mesh for it. Just a standard mesh. Generate mesh. Let's see what has created. What are the statistics? We have 12,197 nodes and 2,508 elements. That's good. Now let's check the orthogonal quality of the default mesh. Now let's close some, and now let's go and change the mesh metric into orthogonal quality. Now as we can see that the orthogonal quality is 0.001, which is enough for our mesh to converge. Okay, so we can also add in sizing, and let's see what happens. Let's change the sizing of it a little bit. Now to select the whole split geometry, we are going to change to box selection and select the whole parts and apply. Before that, we can also create an assignment for it for the materials. Now geometries we are going to also select. We are just making it possible that as we are in the box select tool, may just make it sure that we also apply these things. Now let's apply the mesh sizing over here, and I'm going to select this whole, apply, and since it is 8 millimeters already, now I'm going to do 8 millimeters, and let's create a mesh and check our orthogonal qualities. Generate mesh. We have generated a general mesh over here. Let's see what our mesh quality is. It's 1.3748, means 0.01, which is okay. Our system will converge, but we can do better. I'll go for an 5 millimeter mesh sizing. Let's create a mesh, generate a mesh. Make sure that you have a sufficient orthogonal quality. Now it's 0.04, which is very good quality for me, and I'm very much satisfied by the quality. Let's see how many nodes we have and is our resources sufficient for it. Go into statistics. Sorry if this is disturbing you. We have 9,445 nodes and 1,967 elements. That's quite elements, and we will be able to do it. Just square this number of nodes and you will know how much MB RAM you need, which is just a common practice rule. Now let's add some fixed supports over here. Go into the static structural and right click and insert a fixed support. You can also fix support from here as well, like fixed support. These two supports are added, but we only need one, so I'm going to delete one fixed support. Now let's add that to our bottom. Make sure that you have selected a body type so we can apply to all and change to single select. So we are going to select the bodies of one loop from the bottom. Make sure you press Ctrl key with it. We have pressed a control key and we have selected a loop which will be fixed in the bottom, and apply. Click on the geometry and select these first loop. Make sure you select all faces which are covering. Okay, the whole bottom are selected. Make sure you select all and apply. We have added a fixed support for our simulation. Now let's add a force. Right click, insert a force. Let's insert a force. Let's insert a force from above of 2500 newtons. Let's select the first ring by pressing the control key and selecting every face for it. Let's select another loop that our force is centrally applied and no other has been done. Okay, so we have applied a force. Let's selected our geometry. Now let's apply a force. Now we will be defining our force by components which will be in the negative z direction, negative y direction. As you can see from the coordinates over here, that we will be applying force like this, which is in the negative y direction. This is the negative, this is the positive y, and this is the negative y. So this will be in the negative y direction of minus 2500 newtons. We have added a force of minus 2500 newtons, which you can see from the graph over here. Okay, so minus 2500 newtons applied. You can also see the direction of the force from by here. And okay, we have added fixed supports, we have added forces. Now let's add some results to it as well. I'll add an displacement in the y direction, as we are interested in the y direction only. Directional deformation in the y direction. Now we are going to add a shear stress, because in springs there is more shear stress. So we are going to add a shear stress, which we are only interested here. We can add many other as well, like we von Mises or any other stress, but right now we are only interested to see the directional deformation and the shear stresses produced over here. Now let's solve it. Now here you can see that the deformation is large compared to the model bounding box. This usually appears here, and the reason being is the part is being touched from here to this surface. The parts are being combined, which they should not be combined. Let's play the animation so you can look. The parts are being combined, that's why it is showing a large deflection, and it is showing stresses, elastic strain over here, which you can obviously see. That's not the only reason why you can see large deflection. The large deflection has a totally other topic, which you can see in ANSYS other videos as well. We will cover it in our following series, but here we are going to ignore this deformation and let's proceed further. Now, as we have added a shear stress of 604 MPas now, and compressive shear stresses of minus 589 MPa. Now, as an average is 1.8, which is the difference of that. Now our maximum shear stress that was produced was 604 MPa shear stress, which has permissible and it hasn't broken, so which means that our design is safe, because as we needed to design the spring for 420 MPa, but we have more than enough maximum shear stresses, which is way above the limits, which is 604 MPa, which is good, which means that we are in the safe zone and our design spring is performing well. Now let's see the shear stress diagrams and I shall explain what is happening. Now this is an auto scaled which you can change from here to undeformed. Let's see what is happening in the spring. Now it is saying that the forces that are created are compressive and tensile forces. You can see the inner edges being red, which shows high forces or high compression forces applied, and the outer being also. That's something you have also studied while in the machine design of springs. I'll attach a figure just right over here which can see the force distribution in a spring, which you can now see with contours. Let me just make a contour look over here, contour bands and just no wireframe. We want to see how forces are interacting with our spring. Now as you can see, inner edges are blowing up with the forces as exterior are forcing a negative force. This is our simulation. Now let's see what is the true scale deformation over here and plate. So this is our true scale deformation of our spring. That's good. And maximum is 604 obviously. And the directional deformation, let's see our directional deformation, which is maximum is 5.362 millimeters, 0. That's a very less millimeters, and on an average it's minus 15 millimeters. We can see our deformation over here. Where deformation is at peak and where deformation is very low. So that's it. We have created the simulation and we have checked that our created spring is ready. We can also create reports and attach wonderful pictures to our reports as well, which we will cover in our next video. Thank you for listening to my video. Make sure that you subscribe to my channel Learning Mentor, and we will be seeing more videos about ANSYS, SolidWorks and Python in the future. Thank you very much.